Hello guys, so today we'll be seeing how to train AI model on parallel and distributed computing methodologies and processes. So here we will be seeing some of the major concepts of parallel and distributed computing, and then we will see some code stuff, how to train a simple model with distributed uh, and parallel uh, methodologies or concepts. So I first go through this perplexity chat. So here you see I asked a question: list me tools and libraries and methods to make AI model parallel and distributed while training on multiple GPUs and node or one node or multiple nodes. Okay, so it gave me a type of parallelism. So there are 4 to 5 types of parallelism. So mainly we see the first one is data parallelism. In this, the model remains same on all GPUs, but the data uh, split into multiple chunks, and then it's trained on the uh, it's each chunk is assigned to each GPU. The model on each GPU, it's processes separately, and then the weights uh, are synchronized. Like here, you see the weight gradients are synchronized after each step. So it's map the weights after each step. So this a data parallelism. Then the other one is the model parallelism. In this, if we have a large model, so we can split the large model into into parts, and then we can load each part on uh, a separate GPU for training purpose. So in the above one here, you see there are some framework. We mainly use PyTorch and TensorFlow. Nowadays, you will see PyTorch most of the time because uh, in large language models you will see PyTorch most of the time. Like it's DDP, uh, this DDP protocol as well. So this after that, the model parallelism, as I told you, it's in this the model is splits into uh, on multiple GPUs, and it's loaded by a separate GPU, and then trained each part of this GPU. There are some implementation how it can implement. The model can split horizontally, like layer wise, or vertically across layers, and each GPU process its part of model while sharing parameters during forward and backward passes. So it can share the parameters passes to the model uh, in forward and backward pass. In pipeline parallelism, here in this we can there are we can define we have to define which layers are will be placed on which GPU, and which layers should be placed on the other GPU. We have to define it custom, and we can use some libraries like PyTorch Lightning, and then for TensorFlow we can use TensorFlow function and custom distribution strategies. After that, pipeline parallelism. In pipeline parallelism, here you see the in this method it involves splitting the model into stages, assigning each stage to a different GPUs, and then one stage process its input, and the next stage can start processing its input, leading to a better resource utilization. So for that we use Megatron array, and nowadays you'll see Megatron and Ray. It's most popular nowadays. Tensor parallelism, it can be used for we can use it for large matrix multiplication and deep learning methods and other like simulation as well. So here you see in this we divide tensor parallelism divides individual tensors across multiple GPUs. So for that, the libraries used are deep speed and fair scale provide support to tensor parallelism. The tools use Visa, PyTorch, TensorFlow, Horwood, and then Run AI, Alpha, and some other. You'll be seeing the array. We'll be seeing it in a while. Okay. And then the methods like we have to set the environment and we configure the GPUs and gradient. We can synchronize the gradients while training, and then monitoring and optimization. there are some tools for that as well. So what is Ray? We'll be using Ray. So Ray is an open source framework designed for scaling AI and Python applications, particularly in the context of distributed computing. So it can be used both for it facilitates both CPU and GPU parallelism, and then there are some key libraries we'll be seeing like Ray Ray data. It's a library for uh, which will facilitates data loading, and then uh, and then we have Redtune. We'll be seeing the Red train in this tutorial, and then RedServe and RedAlep. So these are some libraries which are provided by the Red. So the methods we'll be seeing like task parallelism, remote function execution, distributed data uh, processing, auto scaling, fault tolerance, etc. So these all are provided by the array. Then how we can install it by like this pip command. So let's move to one other chat. It's a chat GPT. It is by chat GPT. So here it gave all these similar thing. It gave the NVIDIA Apex as well, and the methods are all the same. And then for multiple GPUs, like in cluster of GPUs, so we will be using. We can use this NCCL. Nowadays, it's popular because most time we are using NVIDIA GPUs, and then MPI, message passing interface, used to internodes communication, and often combined with Howard and NCCL. So nowadays we are using it with NCCL. So the methods used for it, like data parallelism, data model parallelism, and federated learning, it's also one of the one of the important fields you can study. In this, train spread models on multiple nodes and aggregate updates to a central model. And then like for setup, we have to set up the GPUs. We have to install the libraries, and then choose which strategy we will be using, like with multiple GPUs or single GPU, and which one we will be using, like model pipe parallelism or data parallelism, and the other. And then we have to code modification. We will be you have to modify the code and cluster communication. For that, we will be using NCCL for GPUs and Glow for CPUs. And then how we have to synchronize the weights and gradients and model updates across GPU nodes. And then like optimized training, we can use the NVIDIA Apex and the others. And also execution, we have to launch the execution with, for example, with that torch distributed launch. And then for debugging and profiling, we can use PyTorch profiler or TensorFlow profiler, or also NVIDIA Insight. So these packages are come with NVIDIA drivers. Now it's a simple code with a PyTorch DDP. So here you see we call all the libraries, and then we initiate the process group, and then as we set device for current process, we load a low rank, and then we set it up, and then create model and move it to a GPU. We created a model and we loaded a GPU, and then after that, we created an optimizer and also a data loader that can see. And then while training, we also load the data to the GPU as well. So both the model and data should be on GPU. So we can launch it, or we can on a single GPU with this command. So here you can see torch run. Number of processes per node is 4. And it's a single node, so we are not mentioning anything else. And with multiple nodes, we have to mention number of nodes as well. Let's dive into the code stock. Here you can see we will first I run it before starting the recording, because while recording, when I run it, so it stops the recording. So that's why I run all the codes before starting the recording. So here you see we just uh, load the libraries, like we'll be using the array, and then we initiate the array, and then after that we load we have function to load the data set. So we download it and then load it, and then also some pre-process it. And here's our definition for uh, create model. So it's a model stuff. And then here's a function, like function to train a model on subset of data. So here it's a data parallelism technique we are using. So here we mentioned array.remote, and then for that this function specifically. So here model train these are parts of that uh, training stuff or data. So model that create, so model is created for that specific part of data, and then it's compiled, and then it's fit on that specific part of data with just 5 epochs is just for testing. And then the batch size should be 64. So then it will return us the model weights. Okay, so here we load the data by calling that uh, previous function, and then number of workers we assign it 3. So the number of workers we should be 3. So all the data will be divided into 3 splits. So each split will be given to the each worker or node. So after that, here the model training it starts, and then like more train model dash remote. So here you can see, and then after that wait lists. So the in return it will give us a list of weights. So now that weights here there are a lot of strategies how to process that weights. So here we are just averaging that weights for all workers, and then uh, here you can see, and then we created a final model, and we assign it that average weights to that model, and then compile it, and then we can use it for evaluation or prediction. So this is simple, and then we shut down the array. So it's a simple data parallelism technique. So the next one is this. Here you load the libraries, and then load the same dataset, separate dataset, and then the model is the same. So here we are using a TensorFlow distributed multi-worker mirrored strategy, as we discussed in the perplexity chat. Okay, so in this we are using array, and in this we are using TensorFlow distributed training. Okay, so here we load the data set, and then we define a strategy, like train a model with a strategy scope. So strategy scope model, we define a model, and then we initiated a model, and then model got compiled with this specific loss should be the keras loss parse categorical, and then here is the for projects true, or it just I think it's for loss function. Okay, so that we initiated the model training. So the model is trained, and then here's a here we can um, evaluate it. So this is with model this with TensorFlow distributed training. Okay. After that, the third one is this is a simple model data set here for distributed training. So here you can see we just load the array. We are using the array, and then we are using the linear regression. So we uh, load these libraries, and then we initiate the array once again. And then here you see we created a data in this example. We created a data with sample 10,000. Here you see x and y, and then for this specific method we use array dash remote, and then in this we have a data, and then the model uh, linear regression, and then it's fit on the data, and return it's give us a uh, intercept and coefficient. So we created a data set, and then we test size we choose is 20%. So after that here you see it's a splits, and then split the data into three parts for data three nodes. So like in previous first one we use workers, so here are three workers, and then the data splits, and then we train the model with distributed uh, in parallel on different data splits. So here you can see, and then we combine the results. The coefficients you can see, and then there are three nodes, so each node will have its own coefficient intercept. So here are these coefficient intercept for that model. So we shut down the array. So this is just a simple demonstration how we can split the models and how we can split the data between the model. The data parallelism is a bit easier, while the model parallelism is a bit harder, because in that we have to mess with the uh, model layers, and how we can set which layer we can set on which GPU and else. So that's all for this video. Hope you gain some knowledge or some understanding from this video, how we can train these models. Like nowadays we have large language models which are so heavy, the models are so big, so like on just single GPU we cannot train it. So we have to make it parallel for multiple GPUs, and or for multiple or distributed GPUs on multiple nodes on network. So we have to there are a lot of libraries that we mentioned, and lot of techniques in the market, so we can use any of it uh, suitable for us. So thank you for this video. So see you in the next video. Thank you so much.